So we'll write out the first part of this. We have 24 root a divided by root a plus 3 squared, take away root a minus 3 squared. The thing to notice here is that we have a square, take away another square, and this is a very important thing that pops up in maths, and it's the difference of two squares. And this can always be written as the two numbers added, take away the two numbers subtracted. So in this case, the bottom of this fraction, you could actually work it out separately, as I am doing, and it saves writing the whole thing out several times. So for our p, we have the root a plus 3. For our q, we have root a minus 3. So that means for p plus q, we have root a plus 3 plus root a minus 3. And for p minus q, we have root a plus 3 take away root a minus 3. Notice the brackets to make sure I don't muck up the negative signs. So this first bracket here, I have the two root a's, and then I have plus 3 take away 3, so they cancel. I'll put it in a bracket just for my own use to make sure I can check it through if I need to. And then in the second large bracket, we've got a root a and then take away root a, so no root a's, and then we have 3 take away minus 3, so that's the same as 3 add 3, so that's 6. So altogether that gives us 12 root a, which is very nice that something so complicated that we start off with, this thing, becomes something relatively simple. And in fact, when we substitute that back into the original question, this becomes 24 root a over 12 root a, which is of course just 2. Now, this question, you could check your answer because you might end up with getting 2, and part of you might think, yeah, that's what happens in these questions. It looks really complicated and then it simplifies nicely. But what you could do is just pop any old number in. So to do a check, we could say put 7 in. So we'd let a equal 7, and then in our calculator we could pop all this in. And then here's my splendid artwork again as a calculator, and we could see whether that does give us 2 or not. And if it does, then we're almost certainly correct. For part B, we have root 7 plus root 3 as our denominator. And when it says simplify, what it's talking about is getting rid of that denominator. We want whole numbers on the bottom of our fractions. And we again use the difference of two squares here. So we're going to be doing root 7 plus root 3 times root 7 minus root 3. And that will get rid of the roots. I will just write the question down. So we have 3 root 7 plus 5 root 3 divided by root 7 plus root 3. Now when multiplying out a denominator like this, we often see students writing the whole 4 terms that come from the difference of two squares. So I just want to do a quick aside on that. If we have a plus b times a minus b, if we do our 4 bits, your teacher will have done something like that, I guess. And so the first one gives us a squared. The outside gives us a times minus b, so that's minus ab. The inside gives us b times a, which is also called a times b. And the outside gives us minus b squared. And this, of course, then gives us the familiar difference, i.e. minusing, between two squares, a squared and b squared. And my point here is, if you see a plus b times a minus b, there is no need to write out the middle two terms. Just go straight for this. And similarly, if, as you sometimes do in these surd questions, we have a plus b times a plus root b times a minus root b, then we can straight away write that as a squared, take away root b squared, which is just b. Root b times root b is b. And finally, if we have root a plus root b times root a minus root b, then we know we've got the difference of two squares, so it's the first one squared, root a squared is a, and the second one squared, root b squared is b. And this saves a lot of time and bother, and in the end, potentially mistakes. So, going back to the question, the denominator needs to be multiplied by root 7 minus root 3 in order to get our difference of two squares. And as always with a fraction, or if we times the bottom by something, we have to times the top by the same thing so that it stays the same. So what does this equal? Well, on the bottom, strictly speaking, we ought to put brackets there, and it will help us not to make a mistake. On the bottom we have this form, so that is just going to be root 7 squared, which is 7, take away root 3 squared, which is 3. The top is a bit more problematic, but we have 3 root 7 times root 7, so that's going to be 3 root 7 squared. Then we have 3 root 7 times minus root 3, so that's going to be take away 3 times root 3 times root 7. Then we have 5 root 3 times root 7, plus 5 root 3 times root 7. And then at the end we have minus, so it's 5 root 3 times root 3, so that's 5 root 3 squared. And you may prefer to go straight for this next line. The line I've just written is written out pretty much in full on the top, but you can probably see straight away that root 7 squared is 7, so 3 7s are 21. We can see that the 3 and the 7, they're both prime numbers, so there's nothing we can do with that apart from use the general thing, which is, I'll put over here, which is root a times root b is root ab, and you can think of that as coming from the indices rules if you like. The third term, 5 times root 7 times root 3, which is 5 times root 21. And then here we've got root 3 squared is 3 times the 5, 15. And on the bottom, 7 take away 3 is 4. So that gives us 6 plus 2 root 21 over 4, and gives us our final answer of 3 plus root 21 over 2. And for a check here, we could put both the original and the final into our calculator and see if they match. I wanted to add in here the standard expansions that you really should know and recognise, and as well as the difference of two squares, we have, when we have two things added and squared, two things subtracted and squared, and then again the difference of two squares. So this one becomes p squared plus pq plus qp plus q squared, and in fact that's going to be p squared plus 2pq plus q squared. And p minus q becomes p squared minus pq plus q squared, because minus times minus, and that becomes p squared minus 2pq plus q squared. And as we've seen previously, this one becomes p squared minus q squared. I'm not going to do the working out for that again. Now, the point I'm making here is that you need to be able to, well, not need to be able to, but it's advantageous to not have to bother with that middle step when you spot these ones. And remember, you might be starting on this side and going this way, or you may have to recognise one of the forms on this side and go that way, depending on the question. So this question was about simplifying two expressions, and they were both involving square roots. And the square root is the sort of classic number that allows us to distinguish between rational and irrational numbers. And essentially a rational number is a number that can be expressed as a ratio, or in other words as a fraction. And so irrational numbers are numbers that can't be. And in fact in A2 mathematics you will have a look at the proof that some square roots are irrational. But in order to understand that, it's quite nice as a preparation to have an understanding of the various different types of numbers there are. And so we can think of this in two different ways at least, but one way to think of it in terms of human development and in terms of equations. So if we think of the simplest numbers, so they're the counting numbers, so they form a set starting. Some mathematicians include 0 in this and some don't, but they are basically positive whole numbers. And this has a name which is n, and we put a little extra bar down there to show that this is the set of natural numbers. We can imagine early humans starting to count things. They may want to count how many goats they've got, or something like that, but we can see that counting is most likely the first numbers that were used or invented or discovered. And that's another interesting thing you might want to look at. Is mathematics invented or is it discovered? Anyway, we'll leave that aside. Now, the thing about n is that we can use it for solving some equations. So, if we had the equation x plus 3 equals 5, then the solution to that is x equals 2, and that's in the natural numbers. But if we had x plus 5 equals 3, if the only numbers we had were the natural numbers, we cannot solve that, because we would need x to be minus 2 for this to be solved, and we don't have those numbers. So what we can do is expand the set of numbers that we're dealing with, and we could say we've got 0, we've got plus or minus 1, we've got plus or minus 2, etc. Another way that this is sometimes written is ... minus 2, minus 1, 0, 1, 2, ... And this is called z. And we use z because that comes from the German for number, which is Zahlen. Okay, so thinking of our human history story, we can imagine negative numbers possibly coming in for owing things. So you might borrow a couple of goats from your neighbour for the winter, and so you would have minus 2 goats in relation to your neighbour. By the way, this human history thing is not academically researched, it's just sort of off the top of my head imagining, but it's a nice sort of way of looking at it. Okay, so far so good, but what if we had the equation 3x equals 5? Can we solve that? Well, we can't solve that in either the natural numbers n or the integers z, because we now need fractions. So we can define the fractions as the set of numbers of the form a over b, such that a and b are integers, and we must stipulate that b is not allowed to be 0, because we can't have a 0 on the bottom of a fraction. And these are called q, which comes from quotient. And notice again we've got the extra line to denote that it's one of these sorts of sets. Okay, so the quotients are also called rational numbers. Now, we then might have an equation like x squared equals 2. Now it turns out, and I'm not going to look at this here because this is part of your A2 syllabus, so you will come on to that, but it turns out that the solution for this, which would be x equals the square root of 2, plus or minus of course, that number is not a rational number. It can't be written as a fraction. So we have to expand further. Oh, I forgot my story. The rational numbers, we can think of them coming in when things are being shared, which is a very important part of humanity, sharing. So we might share our goats with our neighbour. So if we have 5 goats, we might think of ourselves as having 2.5 goats each. Or not. We might actually be able to think of ourselves as a team having 5 goats between us. But anyway, different ways of looking at things. Okay, so x squared is 2, so that means x is plus or minus root 2 for us. But that means we have to have a bigger set of numbers. Now, this set is difficult to write down in the way we have the other ones. So I'm just going to cheat and just put all decimals. And what that means is any decimal expansion that you could write down, and it could go on forever, it could be non-repeating, so things like pi would be included, but we can just think of it as any sort of decimal expansion at this stage. They're called the real numbers, which is an interesting name because all the other numbers are real as well that we've looked at so far. Although, again, to drift into philosophy, what does real mean? It's context. But that's what it's called nonetheless. Okay, now we get to, what if we have x squared is minus 2? Now, this is an equation that you've been taught is not solvable. Okay, but you have come across the idea of the real numbers. We may be asked to show that an equation has real roots, for example. So that's a sort of hint at the real numbers, but you may not have come across the fact that this equation does actually have solutions. And these would be written as x equals plus or minus the root 2 of I. And I is defined as the square root of minus 1. So this then leads on to the idea of complex numbers. So these are the numbers a plus b times I, where a and b are real numbers. And these are called the complex numbers. Now, going back to our story, the rational numbers might have come from human beings sharing. If we look at the real numbers, well, we already know that there are equations that we can't solve using the rational numbers, so we could think that the real numbers appeared when they were needed to solve certain equations, and we could think of the complex numbers in a similar way. And it turns out that as well as allowing us to solve certain relatively simple equations like x squared equals minus 2, complex numbers are really useful in lots of real fields, as it were, in the real world, as it were. So in electrical engineering they're used, fluid dynamics, quantum mechanics, etc. So they are very useful, in fact essential pretty much within mathematics. So we then have a very lovely chain of sets, because all the numbers that are in the natural numbers are included in this symbol is like a less than sign, but it's for sets, so it means included. So n is included in Z, which is included in Q, which is included in R, which is included in C. And we can write an even lovelier sort of thing, perhaps, or a differently lovely thing, which is that if we write the various sets like this, then we can think of them as being looking like that. Now, the difference of two squares is not terribly difficult to see algebraically, but it's nice to have a look at it geometrically as well, and for this we're going to use Geogebra. So here we have the square a squared, the area of this bigger square, and b squared is the area of the little square. So a squared take away b squared is this sort of L-shaped bit here. So let's have a look at what happens. So first of all, we can play about with it. We can make the big square bigger, we can make the little square smaller or bigger. So let's just leave it like that. Now if we remove the small square, then what's the area? This is the area that represents a squared plus b squared. And we can cut that into two rectangles. So the top rectangle, this height here is the original big square length, which is all that length. Take away the smaller square's length, which is b. So that's a minus b. The length of it is a. And this one has a minus b here and a length or height of b. And we can see this happening now. We can rearrange it to make a big rectangle. So we can rotate this round, and now that's on top of the other rectangle, and then we can slide it along. And so we have the length of this new rectangle we formed from the two parts from our L shape has a length of a plus b and a height of a minus b. And because we know that this L shape came from a squared minus b squared, we also can see that it has an area of a plus b, the length times a minus b, the height. So we have our conclusion there highlighted. And that's rather lovely.